Trigonometry, Chapter 2, Acute Angles and Right Triangles. Section 4, Solutions and Applications of Right Triangles. Video 5, Using Multiple Angles of Elevation. This series is based on content from Pearson's Trigonometry 12th edition by Lial, Hornsby, Schneider, and Daniels. In the previous video, we learned about problems involving angles of elevation and angles of depression. In this video, we learn how to solve a problem that involves multiple angles of elevation. For example, suppose we measure two angles of elevation for a tree. From point A, the angle of elevation is 36.7 degrees. However, 50 feet further away at point, and that should say point D over here, the angle of elevation decreases to 22.2 degrees because we don't have to tilt our head as far when we stand further away. To the nearest foot, how tall is the tree? Well, it looks like just a regular trig problem, but this problem is trickier than it may seem, and here's why. Although we have two right triangles, triangle AB, let me get out the highlighter here. Triangle ABD right here, ABC, excuse me. And we also have triangle, it's a little bit slower than I wanted to be. We also have triangle, where's my highlighter? DBC. So we have two right triangles. But neither one has this 50-foot side as a side in that triangle. The triangle that does have DA as a side, triangle DAB, is not a right triangle. And currently, we do not have the tools to solve a non-right triangles, a deficiency that will be remedied in the future. To utilize this 50-foot in some capacity, we will label AC with length X. Although we're not solving for X, this will give us a way to represent the lengths of two sides in both right triangles. In triangle ABC, the smaller right triangle, the length of AC is X. And in the larger right triangle, DBC, the length of DC is X plus 50. Okay. Now, in each right triangle, we have three parts labeled. And since one of those parts is an acute angle, we can set up a trig equation for each triangle. For example, in triangle ABC, we have angle BAC is 36.7 degrees, AC is X, and BC is H, the height of the tree. Well, since AC is adjacent to the angle and H is opposite, we can set up a tangent equation. Tangent of 36.7 degrees equals H over X. And similarly for the larger triangle, DBC, relative to the 22.2 degree angle, the adjacent side is X plus 50, the opposite side is H, so we can set up tangent of 22.2 degrees equals H over X plus 50. At this point, we have two equations and two unknowns. Here they are. We have a system of equations, and a standard procedure for solving it is to solve one equation for one variable and substitute the result into the second equation. Or equivalently, we could solve each equation for the same variable, then equate the expressions. Now, both equations are easily solvable for H since they're by themselves in numerators, so we'll use that approach. We're going to solve both sides for H. We're going to multiply both sides of each equation by the respective denominators. This will clear the fractions and solve for H. And we get X tangent 36.7 degrees equals H. And we have X plus 50 times tangent of 22.2 degrees is equal to H. Now we can equate these expressions and have this equation that only has X's. Now to solve for this, you're going to be tempted to calculate the values of the tangents. Resist this temptation. We still need to multiply and or divide, so we want to avoid using approximate values. Instead, treat the two tangents as the numbers they represent and do what you would normally do to solve the equation. In this case, that would mean to distribute the tangent on the right. And if we did, we would get an equation that looks like this. Since we have x's on both sides, we want to get them all on one side. So we're going to move the x term on the right side to the left side. Watch quickly, because when I move it to the other side, it will become a minus, and the equal will go right here where the plus is, like this. And then from an algebraic perspective, to make this have a single x, we simply factor an x out on the left side to get x times the subtraction problem. And now we can just divide both sides by the parentheses, and we get x equals this nauseating looking fraction. Except we're not out of the woods yet. We could evaluate it, but We're solving for h. Evaluating this expression will give us an approximation for x, so ideally we don't want to do that. Instead, we want to take either original equation or any version of it, substitute this expression in for x, and solve for h. And this may sound daunting until you recall that we've already solved each equation for h, so we can take advantage of that. The first equation solved for h was x tangent of 36.7 degrees equals h. We'll substitute this value for x into that equation. So grab all this, put it right here where the x is, and we get this mess. Now, personally, I think it looks better if you were to multiply these together. You can treat the second tangent like a fraction over 1 and multiply the tangent into the numerator and get something that looks like that, which is really kind of nice and symmetric. Now, put in a calculator carefully and get that h is approximately 45 feet. Whew. That was quite the problem just to figure out how far apart the trees are. And if you're thinking, why don't we just measure the distance? I'm sorry, how tall the tree was. And why don't we just measure x and do a tangent problem by itself? Because sometimes you can't get right up next to the height of something, as you'll see here in just a second. So it's a nifty little problem because, well, I just think it's a nifty little problem. All right, so this one's for you if I ever get to it. Pause the video and find the height of this pyramid. And notice that we could not just arbitrarily walk all the way up to the bottom of where the height is marked because, well, the pyramid's obstructing our view. Same thing. Pause the video, give it a try. All right, here's your fair warning if you haven't paused the video yet. Solution in 3, 2, and 1. Challenge. Go back and try to generalize this problem, meaning for two generic angles and a generic distance in between, what's the formula that would calculate the height? If you look at this problem and this solution, it should jump out at you.